Right, so now we're just going to talk more about the actual reaction that happens during during a redox reaction, electrochemistry. So an electrochemical cell is a system that has electrodes dipped into an electrolyte, and the chemical reaction either uses or generates electrical current. If we have what's called a voltaic cell, or sometimes it's also called a galvanic cell, that is a spontaneous reaction where the reaction itself generates an electrical current, and you can actually get the energy out. You can use the energy because it generates electrical current. Those would be your batteries. Like batteries are galvanic cells. An electrolytic cell then is the opposite. It's an electrochemical cell in which you have to add electricity to make the reaction go a non-spontaneous reaction. That would be something like if we're trying to plate silver on something, like if you're trying to plate on jewelry, you would have to make it go by creating the reaction. So then we have the two half cells connected in such a way that the electrons can flow from one metal electrode to the other through an external circuit, and that's how you can use the electricity because it's taking it outside of the system. So let's look at figure 19.2 that shows the atomic view of a zinc copper voltaic cell. So here's an example of a voltaic cell. So you can see here on the left-hand side we have the zinc metal ion, not ions, the zinc metal with zero charge, stuck inside a solution of zinc ions, zinc plus 2. Oxidation is happening at this side where zinc is becoming zinc ion. And when that happens, 2 electrons are given off. And so those 2 electrons leave and go to some system. On the right-hand side, we have copper metal, copper atoms, dipped into a copper ion solution, Cu2+. Reduction is happening at this electrode where the Cu2+ are grabbing 2 electrons and becoming Cu neutral. So this is the copper electrode where reduction is taking place. We have to have an internal connection where charges transfer, and we'll talk about that in a little while. So the flow is from the zinc electrode. 2 electrons are leaving it. They're coming into the copper electrode, and this is a voltaic cell. So as long as there's an external circuit, electrons can flow through it. And because zinc has a greater tendency to lose electrons, and this is just an inherent property. We'll talk about how we know that by measuring them, but at this point, just realize that zinc does have that greater tendency. It's not something you can know just off the top of your head. So that means the zinc atoms will lose their electrons to form zinc ions. The electrons flow through the external circuit to the copper electrode, where copper ions gain the electrons and become copper metal. All right. They also have to be connected internally to allow ions to flow between them. And this is because, so we've got negative charge leaving zinc and we have positive charge or negative charge coming into the copper. So like the charge balance is changing between the two. The copper ions are going away, so the the right-hand side is becoming more negative, the left-hand side is becoming less negative. And so we have to have a way for charges to balance that out. So because otherwise the reaction would stop. So in the next two figures, you'll see that the way that we connect the voltaic cell is through something called a salt bridge. So on the left-hand side, picture A, they're not connected yet. So we have our zinc metal dipped into our zinc ion. We have our copper metal dipped into our copper ion. We have a salt bridge which has potassium ions and chloride ions, and it could be any salt, anything that has positive and negative ions. Now, in picture B, once we connect the circuit, oxidation starts to occur at zinc. Zinc becomes zinc 2+, and 2 electrons are released. Those electrons go through the wire. You can see that we can light up a light bulb with it, so we can get work out of it, which we'll talk about later. Those electrons continue on to the copper strip. Now the copper ions are going to grab those electrons and become copper metal, so that's where reduction is happening. But notice that since the positive charge is disappearing on the right-hand side, the positive potassium ions from the salt bridge will flow into the copper side. And you can also see that it's gotten lighter, which means that the copper ions have gone away. It's starting to dilute down. And then since the left-hand side is becoming more positive, the Cl negative ions will flow toward the left-hand side of the picture. So the negative ions will flow toward the left. The porous plug is just there so that the salt doesn't just pour in both sides, because that wouldn't do us any good. So here we have the correct charges flowing in the right way. All right, so the salt bridge is just a tube of electrolyte in a gel that connects the two half cells and allows the flow of ions, but prevents the mixing of the different solutions. So that's what the plugs are for. So the next figure shows the actual setup of a zinc copper cell. So you can see the copper metal stuck in the copper solution, the zinc metal stuck in the zinc solution. They're connected by wires, and then you can see a salt bridge here, which is just like a U-tube, an actual U-tube that has plugs in them and has salt inside them, a salt solution. All right, so let's look at the two half reactions. So zinc again, like we said, zinc becomes zinc 2+ plus 2 electrons. That is the oxidation half reaction. Copper is gaining the 2 electrons to become copper metal, and that's the reduction half reaction. The oxidation half reaction is we call the electrode where oxidation takes place the anode. We can remember this. Oxidation and anode are both start with vowels, and so that's how you can remember which one goes with which. Anode, oxidation. The second reaction where electrons are gained is reduction, and we call this electrode the cathode. So the cathode is where reduction occurs. And those both start with consonants, so that's how you can remember that. So we know that the sum of the two half reactions give us the overall reaction, and because the 2 electrons on both sides cancel, we're all balanced. So this is called the net reaction, and sometimes we also call it the cell reaction. Note that the electrons are given up at the anode, and they flow to the cathode. And so the anode is shown with a negative sign because electrons are leaving it. And the cathode is shown with a positive sign because electrons are flowing to it. So let's look at an example. A voltaic cell is constructed from a half cell in which cadmium metal is inserted to a solution of cadmium nitrate, so a cadmium +2 ion present. The nitrate is just kind of extraneous. Then we have another half cell constructed by inserting a silver metal strip into a solution of silver nitrate. So we have silver +1 ion. Then we take the two half reactions and connect them by a salt bridge. And then we connect them to an external circuit, and the cadmium is oxidized. So first of all, let's sketch what the voltaic cell will look like. Label the anode and cathode, show the corresponding half reactions, and then indicate the direction of electron flow. So the key is we haven't figured out a way to tell. Soon you'll be able to look at tables and be able to tell that cadmium is the one that's oxidized if this is put together. But at this point, I'm just telling you that cadmium is oxidized. So we know that cadmium is the anode. All right, so let's just draw it. Okay, so here's the picture. It doesn't matter which side you put it on as long as you label it correctly, but let's put the cadmium on the left-hand side. So we have the cadmium metal, and it's being oxidized to cadmium ion. So this is the anode, so we label that as the anode, and 2 electrons are given off because cadmium becomes 2+. On the right-hand side, we have silver being reduced, so silver ion plus 1 electron gives us silver metal. We call silver is being reduced, so that's the cathode. So we label that as silver cathode, and we have the Ag ions present. We need to draw a salt bridge in. You don't have to make it that fancy, but just showing that there is a salt bridge. The anode is labeled negative because electrons are flowing from the anode. The cathode is positive, and so we can see the electrons are moving from the negative end to the positive end. Now, what about the complete cell reaction? Well, cadmium is losing 2 electrons, so in order to balance it out, we have to have the silver gaining 2 electrons. In order to do that, we have to multiply the whole thing by 2. So now the 2 electrons cancel on each side, and we have the cell reaction is CD plus 2 Ag plus gives us CD2 plus 2 Ag. All right, now we do have a way that we can draw the voltaic cells, a shorthand way of doing this. The cell, when we had the copper and the zinc ion half cell and the copper is written like this. Notice that the left-hand side, the anode, is always written on the left-hand side. The cathode is always written on the right-hand side. Also notice that the 2 straight lines in the middle indicate the salt bridge that's connecting the 2. And the cell terminals are always at the extremes in the cell notation. So the anode, the terminals, which is where the solid metal is. And then we have a single vertical bar indicating the phase boundary between the solid terminal and the electrode solution. So that's the those lines. So also, just to be a little bit more complete, to fully specify a voltaic cell, it's good to give the concentrations of solutions and the pressures of gases. So for example, here, if we have a zinc being oxidized, we're telling you that it's 1 molar zinc ion, and we have the salt bridge. So we have zinc being oxidized, that's the anode on the left. The single line in between the solid and the solution, and then we have the double line indicating the salt bridge. Then the H plus aqueous solution in hydrogen at 1 atmosphere. And so in platinum, we'll talk about this in just a second, hydrogen doesn't have a metal, so we use an inert metal like platinum as our terminal. So when a half reaction does involve a gas, we have to have an inert material such as platinum to serve as the terminal. So the next figure shows a hydrogen electrode. In a hydrogen electrode, hydrogen bubbles over a platinum plate immersed in an acidic solution. And the cathode half reaction, where it's being reduced, 2H plus 2 electrons gives us H2 gas. So this is just a picture of a hydrogen electrode, a hydrogen half cell. When we want to write a hydrogen half cell, this is how we write it. The notation for the hydrogen electrode written as a cathode is like this. So if it belongs on the right-hand side of the complete cell, so platinum on the left with a single line showing the hydrogen gas and then another single line showing the hydrogen ion. If we want the electrode to be written as an anode, you reverse the notation. So here's some other examples of electrodes, and they're all, in this case, all written as a cathode, but again, for it to be the anode reaction, you would just reverse it. So very similar to hydrogen gas, we have the chlorine reaction, where chlorine gas is reduced to chloride ion. We have the in this case, this is the reduction of iron 3 plus ion to iron 2 plus ion. Notice that in this case, both ions are present in the aqueous solution, and so there isn't a bar dividing them because they're both in the same solution, so there's just a comma. And there's no iron metal in this case, and I believe the reason why you would have platinum rather than iron is that you don't want the iron to reduce down all the way to the metal. You just want to keep the two ions present. You don't want any extraneous reactions happening. And then this is just another typical, here's tin ion reducing down to tin solid. Let's just do an example. Write the overall cell reaction for this voltaic cell. So we have cadmium going to cadmium 2 plus. Since it's on the left, that's our anode. It's telling us it's 1 molar solution. So this is oxidation, anode on the left. And then we have hydrogen ion becoming hydrogen gas. This is the cathode on the right, so that's reduction. So what you would do is you would take the cadmium, gives the cadmium 2 plus ion plus 2 electrons. 2 hydrogen ions plus 2 electrons gives us H2. Because the electrons are the same on both sides, we don't have to multiply by any factor, so we can cancel them out and write them together, and this is our overall cell reaction. So you should be able to take a cell reaction and write it as the in the notation, or take something already in the notation and write the cell reaction.